Hey, welcome back to Calculus. In section 4.5, we're going to continue analyzing the graph of a function using the first and second derivatives. There's really no new material in this section. I'm just going to make this short video with one example and then give you a bunch of problems to practice. But the material that we've developed in 4.3 and 4.4 is really what we need. You're looking at kind of a checklist. These are the things that I would like you to be able to say about a function given its formula. I'd like you to be able to tell me what its domain is, what values it's defined for, what its x and y intercepts are, their coordinates, or the x and y values. Symmetry and periodicity is something that you can use to take advantage of understanding the graph globally, just in terms of sort of part of it. I'll say what I mean by that below. Asymptotes we've talked about, horizontal and vertical, those are limits at infinity and one-sided limits respectively. The increasing decreasing test, the first derivative tells us intervals where the function's outputs are getting bigger or getting smaller. First derivative classifies local extrema. Second derivative handles the concavity, where it's up and down, and also where the inflection points are. All right, so no new information here really, but just sort of a chance to catch up, catch our breath, and analyze this stuff deeply. Let's start by talking a little bit about symmetry. You probably saw this in a pre-calculus class somewhere, but a function is called even if it has this reflective symmetry about the y-axis. Yeah, so the function's graph is a mirror image of itself across the y-axis. Algebraically, that means that the function's output at an input x and its opposite are always going to be the same. So if I picked an x value, its opposite is the same distance away from the origin, but on the other side of the y-axis. And you can see in this picture that the corresponding y-coordinates for that x value are the same. Okay, so that's what I'm writing over here, that the y-coordinates for x and minus x are always the same. When that's true, you have some symmetry, an even symmetry in particular. And why would that be useful? Well, if I analyze the graph carefully, say on one side of the y-axis, then I can just transfer all that analysis to the other side because it looks exactly the same. Okay. Odd symmetry is a little different. It's rotational symmetry about the origin. If you spun that graph around the origin 180 degrees, it would land on itself. So the algebraic condition for odd is that the function's value at the opposite of x is the opposite of its value at x. So to illustrate that, if I pick an x here, its opposite again is equal distance on the other side of the axis. And you can see that these two outputs, f of x and f of minus x, are opposites of each other, right? So whatever this y coordinate is over here at x, the y coordinate at minus x is its opposite. That's what this equation says. What are examples of even and odd functions? Well, among most functions are neither even or odd, but some important ones. The cosine function is an important even trigonometric function. And then in polynomials, if all of your exponents are even, then you have an even function. I think that's why they're called even. Odd functions, the important one in the trigonometric family is sine. Sine is an odd function. And then if you take powers of x where the exponents are all odd, then you'd have odd functions among the power functions, or linear combinations of those things. All right, so that's just a little bit about symmetry. It can be used to exploit your work if you know a function is symmetric. What about periodicity? Periodicity literally means that there's some number. In this picture, the number is called p, and the function is periodic if its value at x plus p is the same as its value at x. So that's kind of a horizontal symmetry. If you translate, in this picture, you're kind of looking, they've picked a value of a, and if you look at all the values on the graph between a and a plus p, you get some shape like that. And this graph is just a translation of that shape. Yeah, if you move p units to the right, over and over and over again, p units to the left, over and over and over again, you just repeat that shape. So again, if you were analyzing such a function, if you just analyzed it on the interval from a to a plus p, if you knew how it works there, then you know how it works everywhere by extending it indefinitely in both directions. Certainly among our functions that we're going to talk about in this class, sine and cosine are important examples of periodic functions. They have period 2 pi. The ratios of them, secant, cosecant, also have period 2 pi. Tangent and cotangent, because they involve both sine and cosine. This is kind of a nice algebraic puzzle, but they're periodic, but their period is just pi. Okay, so if you have some periodicity, you can exploit that. So let's look at just one example. I'm going to kind of go through all the computations with you, so I hope this doesn't get too long, but I'd like to analyze the graph of this function. So I'd like to go through that checklist. If we kind of scoot back to the beginning of the video here, what do I mean analyze it? I want to know, well, what's its domain? What are its intercepts, symmetry, asymptotes, and all these intervals of decrease, increase, concavity, everything. I want to know everything. All right. So let's start to do it. We don't have to do it in any given order, but I'm just going to kind of use that checklist as a reminder for myself here. So what about the domain? The domain of this function? Well, the domain of the function is any value you can evaluate x at. Cosine and sine have domain all real numbers. What we'd have to worry about here is if this denominator could ever be 0. But since the sine function is never equal to -2, that denominator is never equal to 0. So the domain of this function is all real numbers. As an interval, I can write that like this, minus infinity to infinity, or if you prefer, you can just write this symbol, this R. It stands for all real numbers. Okay, good. So that's its domain. How about its intercepts? The y-intercept is always the easiest one to calculate. If 0 is in the domain, the y-coordinate of the y-intercept is the function's value at 0. All right, so to calculate that y-intercept, I'm just going to plug in 0 to the function. I get cosine of 0 over 2 plus the sine of 0, and that's, excuse me, my first mistake here. The cosine of 0 is 1, the sine of 0 is 0, so the y-intercept's y-coordinate is 1/2, right? So this function's y-intercept as a point is the point 0, 1/2. Nice. So we have that. How about x-intercepts? X-intercepts, you have to solve the equation, how could f of x equal 0? X-intercepts are about putting the output equal to 0. All right, well, that's if and only if the numerator of our fraction is 0. Cosine of x is 0. Well, cosine has infinitely many values of x that make it 0. But here, I'm going to exploit the periodicity of this function. Sine and cosine are 2 pi periodic, and so will this function. So we're just going to evaluate our x's here for a moment between 0 and 2 pi. So for the rest of this stuff, I'm just going to write answers to equations like this one for x's between 0 and 2 pi, because I can recover the rest of them by periodicity. Okay, so the cosine of x is equal to 0, given that restriction. Well, when is cosine 0? It's 0 when x is pi over 2 and 3 pi over 2. In the interval from 0 to 2 pi, those are the only two values. So our x-intercepts are at the points pi over 2, 0, and 3 pi over 2, 0. Yeah, so I can talk about the x-coordinates of the x-intercepts, or I can talk about the intercepts themselves. The intercepts themselves are points in the plane. All right, so that gives me some information about that. So there's our domain, our intercepts. What about asymptotes? This thing doesn't have a horizontal asymptote. Yeah, the limit as x goes to infinity of this thing doesn't exist because the numerator and denominator just keep oscillating between -1 and 1. So I'm going to have to scroll here. So you're going to have to remember what our f of x is. But the limit as x goes to infinity of cosine of x over 2 plus sine x doesn't exist, because the functions in the numerator and denominator just keep oscillating. So there's no horizontal asymptote. No horizontal asymptote for this function. There's no values that make the function undefined, so there's no vertical asymptotes. So we don't have to take any limits when we analyze this function. So it's time to start thinking about intervals of increase and decrease. It's time to start thinking about derivatives, right? So maybe just for convenience, I'll rewrite the function itself so we don't have to keep scrolling. So there's our function, and to take this function's derivative, we're going to need to use the quotient rule. I want to take this function's derivative and simplify it as much as possible. So let's start. It's 2 plus the sine of x times the derivative of cosine. I'm going to do this differentiation on the fly to keep the video a little bit shorter. Derivative of cosine is the opposite of sine. and then I subtract the cosine times the derivative of the denominator, which is cosine. All of that has to get divided by the denominator squared. All right, I need to simplify that thing a little bit. Let's distribute out our numerator. So we get minus 2 sine x minus sine squared x minus cosine squared x. All of that is over 2 plus sine x squared. Yeah, and if you factor out a -1 out of that numerator and use the fact that sine squared plus cosine squared is equal to 1, that thing will simplify a little bit. You'd have minus the quantity 2 sine x plus 1 all over 2 plus sine x squared. All right, and that's a pretty nice form for us to analyze. We can see that the denominator is never 0. So there's no bad critical points. And let's actually find them right now. Again, with the restriction that x is between 0 and 2 pi, this thing is equal to 0 if and only if its numerator is. And that's if and only if the sine of x is equal to -1/2. And so from unit circle trigonometry, there's two values of x between 0 and 2 pi that make the sine equal to -1/2. And those values of x would be, well, the first one is 7 pi over 6. And the second one is 11 pi over 6. All right, so these are going to be the two values that we mark on our sign diagram for f prime. Our sign diagram for f prime. Let's actually make it right now, and maybe we'll copy and paste it or something like that and drag it down. So again, I'm only talking about things from 0 to 2 pi right now because we're going to exploit some periodicity. We just found out that at 7 pi over 6, the first derivative is 0, and it's 0 again at 11 pi over 6. These are just schematic. You don't have to draw this to scale if you don't want. And then let's look at this derivative. Well, you can do this by choosing points. So just literally choose values of x in each of these three intervals, plug them into the derivative expression, and record whether or not you get something that's positive or negative. I'm going to look at this a little bit less computationally. I'm looking at the denominator, and I see that that's always positive. And this minus sign makes the sign of the numerator the opposite of what's in here. Yeah. So if x is between 0 and 7 pi over 6, then the sign of it is bigger than -1/2. Yeah. So 2 times that is going to be bigger than -1. And if you take something bigger than -1 and add 1 to it, you're going to get a positive number. But this minus sign out front negates that. And so we should get minus signs. We should get minus signs for the first derivative out there. You can do that again by plugging in numbers, right? So we get some minus signs on that interval. Likewise, you can check that between 7 pi over 6 and 11 pi over 6, this derivative will be positive. Choose values if you like. I'm doing it by just thinking that the sign is less than -1/2 in there. So 2 times it's less than -1, and so on. And then you'd have a minus sign over there. All right, so we'll come back and copy this derivative, but that's going to be enough information to tell us where this thing is increasing, decreasing. We can write it down now if you want. Why not? So just on 0 to 2 pi, just on that interval, f is increasing on the interval from 7 pi over 6 to 11 pi over 6. And it's decreasing on the interval from 0 to 7 pi over 6, and again from 11 pi over 6 to 2 pi. Oops. 2 pi. All right, good. What about extrema? Should we use some first derivative test right now? This function was decreasing and then increasing. So what kind of extrema do we have at 7 pi over 6? We must have a local min. We must have a local min at 7 pi over 6. It was increasing and then decreasing, so we must have a local max at 11 pi over 6. Let's write that down. So we've got a local minimum at x equals 7 pi over 6. We've got a local maximum at x equals 11 pi over 6. All right. You can get out your calculator if you want and check that f of 7 pi over 6. I did this on side work, so I'm just going to write it down. It's minus 1 over the square root of 3. Check that with your calculator. F of 11 pi over 6 is positive 1 over the square root of 3. All right, so those are our minimum and maximum values. Outputs, maximum values, minimum and maximum are inputs. Nice. All right, so we've almost completed the analysis. We need the concavity. For the concavity, we need the second derivative. And for the second derivative, we need to be able to differentiate the first derivative. So let's copy this first derivative. I can just sort of use some whiteboard magic and bring it down here. Give ourselves a little bit of room. This was f prime of x. So for f double prime of x, we have to carefully differentiate this thing. It's going to involve lots of differentiation rules. And we're going to have to try to simplify it. So I'm going to park that minus sign out front and then start using the quotient rule. Okay, so I have to take the bottom, that's 2 plus the sine of x quantity squared, and multiply it by the derivative of the top. The derivative of the top is 2 cosine x. And then I have to subtract that top, 2 sine x plus 1, times the derivative of the bottom, which involves the chain rule. The derivative of the bottom is 2 times the quantity 2 plus sine x to the first, times the derivative of 2 plus sine x, which is cosine x. Okay, so there's my, numerator of my quotient rule. The denominator, I have to square 2 plus sine x squared, so I'll have 2 plus sine x to the fourth power. And now some algebra. Let me at least kind of highlight and let you show you what I'm thinking about here. I see a 2 plus sine x. There's actually two factors of them right there. There's a factor of it right there. So I'm going to factor those out, and it's going to cancel one of the four downstairs. Okay? So I'm going to just kind of try to talk you through this. I think the best thing to do is probably stop this video and simplify this thing yourself, because trying to do algebra the way I do it is like walking in somebody else's shoes. But I'm going to try to show you how I think about this. So I'm going to have a 2 plus sine x cubed downstairs after I factor that stuff out and cancel it. But then upstairs, I would still have one of these factors, which I need to distribute this 2 cosine through. So I'm going to have 4 cosine x plus 2 sine x cos x. And then up here, I don't have this term that's underlined in green. I factored it out, but I do have everything else. And watch out, there's a minus sign. So I have minus 2 sine x times 2 times cos x. So that's 4 sine x cos x. And then I have minus, again, let me just help you see what I'm talking about, minus cos x times 2 times 1. That's minus 2 cos x. All right, can do a little bit here. We can simplify some or gather some terms in that numerator. 4 cos x minus 2 cos x is 2 cos x. And then positive 2 of those things minus 4 of them, well, that's minus 2 of them. So it's simplifying pretty nicely. That's over 2 plus sine x cubed. We can factor out a 2 cos x out of the numerator. Why not? Trying to see where this thing is equal to 0 in a second here anyway. So factoring it is always the way to go. And that would be 1 minus sine x. Okay, so there is a nice simplified expression for our second derivative. Maybe I can remind you that this is f prime prime of x. And then what do I want to know? Well, I want to know where it's 0 and where it's not defined. First of all, 2 plus the sign is always positive, so it's always defined. So the only thing we have to worry about is how this thing can be 0. Well, and it can be 0 if and only if the cosine is 0. That's one way. Or that parenthesized expression 1 minus the sine of x is 0. Okay, the cosine is 0 when x is pi over 2 and 3 pi over 2. Remember, we're only thinking about the unit or the interval from 0 to 2 pi. 1 minus the sine of x is 0 when the sine of x is 1. The sine of x is 1 only when x is pi over 2. So there's some redundancy here. So we make a sign diagram. Again, we're only thinking about the world from 0 to 2 pi. This is a sign diagram for f prime prime. And I mark the values we just found. Pi over 2 makes the first derivative 0. 3 pi over 2 makes the first derivative 0. And then you have to carefully do the signs. You have to carefully do the signs. So I'll let you check that these signs are going to go, just choose specific values. Pick a value in here, pick a value in there, pick a value in there. I'm just going to tell you how I'm thinking of it. Between 0 and pi over 2, well, the cosine's positive. 1 minus sine is always negative or 0. So it can't contribute to positives. This stuff down here is always positive. So this minus sign out here would give us a negative in that interval. All right, but you can use specific values to do that. You'll see that you'll get positives in here, and you'll get negatives in the third interval. All right, so filling in the signs. What does that tell us about the concavity? Well, remember, we're concave down wherever the second derivative is negative. We're concave up wherever it's positive. And we have inflection points wherever it changes. All right, so we can just summarize all of that business by writing it down. So f is concave up on the interval from pi over 2 to 3 pi over 2. F is concave down on the interval from 0 to pi over 2, together with the interval from 3 pi over 2 to 2 pi. And we have inflection points when x is pi over 2 or 3 pi over 2. Pardon me, 3 pi over 2. And the value you can check of those inflection points, you can check that f of pi over 2 and 3 pi over 2 are 0. So the y coordinates at those inflection points are 0. All right, so that's a pretty thorough analysis of the function. Let's switch over to Desmos and see if what we see agrees with what we were looking at. I don't quite have Desmos ready, sorry. I should be a little bit more prepared here, but let's see what we're going to see. Here we go, I found it. Okay, here's a Desmos window over there. You can see it. I don't have anything typed in it yet. I need to put this function. What is this function that we're talking about? We were talking about the function cosine x over 2 plus sine x. So let's just type that in. Cosine x divided by 2 plus the sine of x. Desmos knows what I mean. Let's get this panel out of the way and let's see if it kind of makes sense. Here's a little Desmos trick for you. If you want to see the actual values of the trig functions on those axes down there, if you go to your settings and on the x-axis, make your step something that you want to see like as a multiple of pi. So what did we want? We wanted the trig values. We had a couple, those pi over 6s. So maybe I'll make my step pi over 6. Something like that, yeah? And then let's first just look from 0 to 2 pi. This is what we were analyzing. So here's our graph. Let me zoom out just a little bit. Sorry about that. Well, so what do we know? We said that the y-intercept was 0, half. Should we start plotting some of these things while we're talking? So the y-intercept is 0, half. Yeah, that looks like it's right to me. Yep, absolutely. Remember what we said the x-intercepts of this function were? The x-intercepts of this function were things like pi over 2, 0. Yeah, looks right. There was one at 3 pi over 2, 0. That looks right. I'm just going to leave the colors so we don't have to worry about them. Good. There's no asymptotes. And then can you see the periodicity? So what this function looks like from 0 to 2 pi, it just repeats. It just repeats itself. Let me change the y scale. Sorry, I know this is kind of annoying to watch. I should have had this all ready to go, but I didn't. I like that a little better. In fact, I even like minus 1.5 to 1.5 even better. Brings out the, right? So while you can't really see the periodicity all that well here, let's make this thing go from, say, minus 4 pi to 4 pi. Good. Okay, so here's the interval from 0 to 2 pi. That's our one period. Nice. And you can see the thing just repeats. So analyzing this everywhere. Where did we say the local extrema were? There was a local extrema at 7 pi over 6, if I recall correctly. And if I further recall correctly, the y value there was minus 1 over the square root of 3. Let me see if I can put that in to Desmos and make it happy. Yeah, there's that extrema. If I put the label on it, okay, that was our local minimum. 7 pi over 6, there's the decimal value for minus 1 over the square root of 3. We said there was a local maximum at 11 pi over 6, if I'm not mistaken. I'm doing this from memory, so I hope I'm not mistaken, but 11 pi over 6, oops, 11 pi over 6, comma, the value was 1 over the square root of 3, if I recall correctly. There's your local max. Okay, so we can turn these points labels on if we want to see their coordinates, or we can write, let's call it the y-intercept. This is a cool way to create some nice homework solutions. Yeah, what's this point? Let's turn its label on. It's an x-intercept. This one is an x-intercept. This one is a local min. This one is a local max. You can see that those are actually global. It takes the graph to see that. Good. And then by periodicity, we can push all of that out. Where were the concavity switches? The concavity switches were at the intercepts. Notice that here at this first x-intercept, we're switching. This first x-intercept is, it's also an inflection point. Yeah, the second one is as well. Inflection point. Cool. Let me just get rid of that. Maybe turn the contrast up a little bit here and we can enjoy. That was a thorough analysis of this complicated trigonometric function using our ideas from calculus. Okay, so this video is getting a little long. I hope that's useful, and I hope you're going to practice this a ton in section 4.5 so that you get comfortable and confident at it.